All right, I'm going to go through some stuff on light waves. So, speed of light in glass, which has an index of refraction of 1.5. So, this is our N equals C over V equation. N is my index of refraction. That is a number, it's kind of like a ratio that tells me how dense a medium is and how much the light is going to slow down as it passes through that medium. C is my speed of light in a vacuum, 3 times 10 to the 8th meters per second. Speed of light in vacuum. And then V is my speed of light in my whatever material it is. In this case, it's glass. Okay. So we can use this equation to solve for N. We can also swap these two and use it to solve for a speed if we're given an N value. Okay, so that's what we're doing here. So we've got 3 times 10 to the 8th. That's like our top speed. Okay, you can't go faster than the speed of light. And we're going to divide that by 1.5. Remember, you're dividing a huge, enormous number here by a really small number. So what you can do is just divide 3 by 1.5. That's going to give me 2. And then I'm just going to tack on that times 10 to the 8th because all those digits are still going to be there. So that's an easy way to do this type of math without having to mess with the 10 to the 8th. You don't really have to do anything with it. You're just carrying it along. If we were solving for an N value, then we'd have 3 times 10 to the 8th. We'd be dividing by some kind of speed, which would also be a times 10 to the 8th. And then those would cancel. So you really actually don't have to do anything with the 10 to the 8th in these questions, which is helpful. So that's going to be 2. Okay. So here is a light ray going from one medium to another, and it's bending towards this normal line. We talked about having this perpendicular line. What does that tell us when it bends toward this line? Okay, that tells us that it's going from a less dense to a more dense medium. Okay. And that's because it's slowing down. It's bending because it's slowing down. Its speed is changing. Its speed is dropping because it's going from something, maybe say it's going from air into water. Okay, so it's going from something less dense to more dense. So less dense to more dense and slows down. Looks like that would be A. So if my ray bends towards this normal line, then we know that we're going into something that's more dense. Okay. Okay. 2 students gather data. They record angles of incidence and refraction. What's the likely identity of the unknown liquid? Okay, so this is a Snell's law where we use N1 sine theta 1 equals N2 sine theta 2. We're solving for N2 here. They said use N1 is 1, so this is 1. I don't have to worry about that. I'm given several angles here. I can do this with any of them. I'm going to get my calculator out. I guess, I can kind of choose which one I want to use, but remember, angle of incidence is your incoming angle. So that's this angle. And then angle of refraction is the one that you're bending towards as you come from material 1 to material 2. These are just numbers. We're just getting the sign of a number, and then we're solving for another number. We're doing this in degrees. Okay, so watch out for that. So let's just try the first one. Sine of 5 equals N2 times sine of 3.62. I'm just getting those straight from this table. Okay. If I want to solve for N2, I need to divide both sides by the sine of 3.62 because, again, these are just numbers. The sine makes it look a little more intimidating, but we're just going to deal with them like they're regular numbers. So those two cancel. Okay, so sine of 5 divided by sine of 3.62. And that gives me 1.38 or 1. Yeah, so 1.38 looks like milk. Milk. And we could try that with another set of angles. So let's try sine of 10 divided by sine of 7.22. Gives me same thing. Okay, so they give you this table. You really don't need all the values in this table, but you can double check using the others. So okay, so then we've got this double slit experiment. This is where light was passed through two slits and we get this interference pattern. The light waves bend as they pass through the slits because of what's called diffraction. That means the waves bend as they go around basically a barrier. And other types of waves do this too, like sound waves. This is where they saw that light behaved as a wave, and they were like, hey, we thought light was a particle, so light's kind of both. How would the pattern change if these slits were moved farther apart? So now imagine you're taking these two slits and you're moving them farther apart. When you do that, you're going to get more interference because as these waves go through the slits, they're going to bend, and where they're bending and curving and overlapping each other, we get these constructive interference, these bright bands, and we get these destructive interference dark bands. Okay. So if the slits are moved farther apart, we're going to have more interference. We're going to have more bright bands and narrower dark bands because we're going to have more interference. Okay. And we saw that when we did the simulation on this. We really didn't have a way to do this other than a simulation. So, okay, a beam of white light hits a prism. What describes what happens? Remember, white light includes all of the colors of the visible spectrum, which is our Roy G. Biv colors. And so when white light hits a prism, the light's going to be broken apart into these separate wavelengths. That's called dispersed. Okay. So the light's going to be dispersed into individual colors. And then how much they bend. So really these are waves that are bending as they hit a glass prism. How much they bend depends on their wavelength. Okay. Red has the longest wavelength, so it's going to bend the least. And then so on through the rest of this. Violet's going to bend the most. So remember, this looked like we saw a video of this where our white light's coming in, and then as it gets broken apart, red is going to be bent the least because it's got the longest wavelength. Violet was down here at the bottom and gets bent the most as it hits that prism and breaks apart. 3 primary colors of light and what we get when we combine them all. So remember, this isn't like primary colors from, elementary school or whatever. These are wavelengths of light. Okay, that's what gives us the colors of the visible spectrum, are the wavelengths. And so the primary colors are red, green, and blue. That goes back to Roy, red, green in the middle, and then blue being part of Biv here at the end. And when we combine them all, we get white. Okay, let me try and speed through these last couple questions. Polarizing filter. Remember, light's got these two components, electric and magnetic. They're perpendicular to each other. So if we want to block one of those, say we want sunglasses to block out harmful light, then we're going to block one of those two directions. And in this case, this is a vertical filter. So it's going to let the vertical piece go through and it's going to block the horizontal piece. Okay. You could swap it and do it the other way. It just depends on what you want to block. What does the double slit diffraction experiment tell us about the nature of light? So I already kind of talked about that, is that it tells us that light is a wave, okay? Because, let's see, light, the best one for this is D. Light is a wave because light bends as it travels around an obstacle and creates a pattern due to interference. So interference and bending, this diffraction, are behaviors that other waves, that scientists had already seen those from other waves, and then they saw it with light. So they know that light's got wave properties. And why does it have these components that are perpendicular? I talked about this as well. Light is both electric and magnetic. That's why we call it the electromagnetic spectrum. So it's got these components of each, and they are perpendicular to each other, like we saw in this graphic here. So, okay, so that's light waves.